Okay, so here let's take a look. We're going to jump in and work on, oops, this should say 1.6 piecewise functions like it says up there. And these piecewise functions, you have seen them before. You perhaps have not studied them as much as we will in this course, but just a quick review because we all should be pretty familiar with how these work as we work through advanced functions. So we'll warm up here, we'll start, and we'll try and find the inverse, just like from section 1.5. The inverse of f at x, if f at x here is a transformed radical function. Okay, so when we're finding the inverse, the first thing we always do is we write out, and again, we must write this out, we switch x and y. X and y, good. Now we have here x equals -1/2. This times the square root of -3 times y plus 2 minus 5. Good. I should have left a little bit more space here, but I did not, and that's okay. We're going to shift this around here. I know, rather than restarting the video, I'm feeling a little bit, feeling like we can do this on the fly. Good, so we can now add 5 to both sides. So that is x plus 5 equals -1/2 times the square root of -3 times y plus 2. Multiply both sides by -2. That is -2 times x plus 5. We're working our way forward here. Times the square root of -3 times y plus 2, all square rooted. Now I can square both sides here, leaving me with -2 times x plus 5, all squared. Now if I square all of that, we can simplify that a little more later. All squared equals -3 times y plus 2. And we can keep pushing on forward. That is -1 divided by 3 times -2 times x plus 5, all squared, equals y plus 2. And to finish it off, we're working with here -1/3 times -2 times x plus 5, all squared, minus 2 equals y. Good. So we've performed our operations in our inverse operations in the opposite order. Now, from this point forward, we need to be a little bit careful, right? Because where we started here, if we take a look, we have a radical. Now, not all inputs can be handled by a radical, right? The limit is that a radical can only handle positive input values. This input here must be greater than or equal to 0. So that is our input, -3 times x plus 2 must be greater than or equal to 0. So let's try and find where this is equal to 0, okay? So if we rearrange this, then we're working with, we divide both sides by -3, leaving us with x plus 2, and that means where x equals -2, this equals 0. And we can double check on which side of this will be working, right? Since we're multiplying that by a negative here, that means our input must always be x must be less than or equal to -2. If you're not sure how that works, spend a moment, try and wrap your mind around it, or else throw this entire equation into Desmos and check its domain. Or else we can, if you ask about it in class, then we can go over that as well. If we sketch our inverse, or we sketch our original function, it should be somewhere from the point x equals -2, y equals -5, so something like this, and it will be, working down in this direction here. And if we just do a quick sketch of our inverse, we're working from the x value, x equals -5, and we'll be looking at only one arm of a parabola. Since there's only that one arm, we need to limit this right here. This restriction will be x is less than or equal to -5. If you're not sure on that, that's okay if you're feeling a little bit wonky about that. But what I do want you to see is just this notation here where we're working and we have a function and it must have a restriction in here in order to be an accurate representation of an inverse. If we're using this with a restriction, we write out the equation here on the left, a comma, and then the restriction. Okay, we will see that theme pretty common as we work forward here into our piecewise function. So a piecewise function is a function made up of two or more, we call them subfunctions, where each of these subfunctions is defined for a certain part of the function's domain. Okay, we'll call that a subdomain. So that means that for a certain part of the domain, we use one function, and for a different part of the domain, we use another function. So that would look something like a piecewise function would equal, and then we have a squiggly bracket, and we might say f1 of x, where we have a restriction, or rather, I'll give us some square brackets. What we would have here is a subdomain. And then we might have another function, another input, f2 of x, where there's a second different subdomain. Okay, now you should have seen these before. If you've not played around with them, then you will be getting comfortable with them during this lesson. Now, example 1. So the cost of a cell phone plan, okay, is that there's a flat rate of $30. Let's go with our highlighter here. A flat rate of $30 for up to, if the buyer uses up to and including 2 gigabytes of data. Okay, now a flat rate of $50 user would have to pay if they're using from 2 gigabytes to 5 gigabytes of data, and a fee of $60 plus 25 cents per additional gigabyte if they're using more than 5 gigabytes of data. So something like this, if we're just going with a very rough sketch, then what's actually going on here is we'll have the input on the bottom. So that's the number of, the amount of data. And our units here would be gigabytes. And along the vertical axis here, we'd be working with cost in dollars. So, and again, this is extremely rough, and that's okay. So for up to and including 2 gigabytes of data, so we'll say 2 gigabytes of data, then it costs $30. No matter what, if you use 0 gigabytes of data, it costs $30 for the cell phone plan. If you use up to 2 gigabytes of data, it costs still $30 for the cell phone plan. So our cost would be something like this, and since it says up to and including, then we would have a closed circle there, and we'll say this is, $30. Now, after 2 gigabytes, all the way up to 5 gigabytes, so we'll give us a 5 gigabytes right here, all the way up to 5 gigabytes, it's going to cost $50. So that means we're working here, it would have to be an empty circle, right? Because we know it, if it right at 2 gigabytes, it does not cost $50, it costs $30. And then we can go all the way up to here, and again, a closed-in circle, because if they're using 5 gigabytes of data, then it's going to cost $50. And then $60 plus, here we need to be careful, plus 25 cents per additional gigabyte for more than 5 gigabytes of data. So we would be looking at something that looks like here a bit of an empty circle and a very slow increase as it goes off. Okay, so this here, what we've just sketched, is what we call a piecewise function, where it uses one input for a certain part of its domain, and it uses a different input for another part of its domain, and it uses, in this case, a third input for another part of its domain. Now, algebraically, we would represent this as, and we can use cost as a function of data, C at D, equals, and then we have our squiggly bracket here, give ourselves a little bit more space, equals $30 if the data is less than or equal to 2 gigabytes, and the cost is $50 if the data is, if the data is greater than 2 gigabytes and less than or equal to 5 gigabytes, and the cost is $60 plus 0.25, because that's 25 cents for each additional gigabyte of data. So that's going to be if there are 6 gigabytes of data, then they'll be only charged for one of them. So that means their data minus 5 gigabytes that they get covered in the plan. And the restriction here is if data is greater than, just greater than 5. Okay, so this is an example of an algebraic representation of a piecewise function. Okay, so hopefully it's at least ringing some bells. It's reminding you of what you've covered in the past. If not, I'm hoping you're able to follow this. If you're struggling with it, again, we will go over it. We can help you out. Next, example 2 here. So we're going to graph another piecewise function. This time we're given the piecewise function in algebraic notation, right? In algebraic representation, like we worked to find last time. Here we're given an equation. So we'll try and plot this right away. So if x is less than or equal to -2, so we'll call this -2. If x is less than or equal to -2, then f at x equals 3. Good, so we'll call this 3 here. And this will go off towards -infinity. It's less than or equal to, so we have a filled in dot here. And then we go on to the next part of the domain. So the next part of the domain is between x is equal to 2 or -2. So that means that for this entire portion of the domain, we're going to be following this part of the input, which is x squared minus 1. Now, x squared minus 1, hopefully you can sketch something like that relatively easily. What we do need to double check here are where are the endpoints, because I want to know, will my subfunction meet up with the other subfunction, with the first subfunction, or will there be a little bit of a gap between them? If there's a gap between them, we do have a term for that. We went over that during the 1.3 lesson. So x squared minus 1, what we're looking at, where if x were to equal -2 here, I can substitute that in, f at, and really I'll say f2, because it's my second input function of x, of -2, equals x squared minus 1, except we're substituting in -2, so equals -2 squared minus 1, and that is 4 minus 1, and that equals 3. Good, so it will completely match up. Now, that means as well, I know from the symmetry of a function like this, it's also going to come up to 3 on the other side. Now, there is no equals sign here, so I'm going with an empty dot at x equals 2. Good, then we can push on forward, and we can find that f at x equals 2x, where x is greater than or equal to 2. So for this final part of the domain, we're working with the input f at x equals 2x. Well, let's double check where that's going to be right at x equals 2, just again, so I know if there's going to be a gap here. So f3 at 2 equals 2 times 2, and that equals 4. So that means there is a bit of a gap. We're going to have a filled in circle here, and then a linear increase, something like this. Now, from this, we can see here there is we can draw much of the function without lifting our pen from the page, but not the whole thing, right? If I'm starting to draw from -infinity, I can draw, I can go along, I can go along, I can go along, and then we call this part a hole, and we call this part a break, right? Because I have to lift up my pen from the page and then move it before continuing to draw. So if we have a break, then there is no continuity. Okay, this function is not continuous. So we would say, no, this function is not continuous. Explain, our explanation is there is a break at x equals 2. Fantastic. So we've described its location. We've described what's going on. Fantastic. Now we can push that forward even more, and we can try and determine from a graph here an algebraic representation. So this will be the last example we go over here. Now, we are going to take some liberties. I know it's not in good quality. Sometimes when you're working in math, it's not the best of quality. In general, if you're working a job and you're trying to solve something, often graphs you're going to need to interpret on your own. So let's try that out here. We can see, I want you to take a look and maybe pause the video and try and figure out how many subfunctions there are. How many subfunctions are we going to need to represent what's going on here? And I'm hoping you can see that there are 3. So we're working here with f at x equals, and we need to find f1 of x we need to find f2 of x, and we need to find f3 of x. Now, we can see as well their domains, right? f1 of x, if I'm going from left to right along here, their domains, I'm going to be following my very first, here, let's go in yellow, my very first f1 of x, looks like it has the domain up to, and we can choose here whether it's including or not, because it looks like both f1 and f2 meet at the same point. But where x is less than or equal to -1 would be an appropriate domain here. So let's, I'm just going to color that a little bit in yellow so we can match it. We'll see, I'll do that afterwards. Here we are. So where x is less than or equal to -1. That's our first subfunction. Our next subfunction is going to be in between -1 and it looks like +2 here. So since, now we need to be a little bit careful, since I chose less than or equal to for my first domain, I must say less than, sorry, x is greater than -1, not or equal to, because I can only have one inputted function, or sorry, one output function for each input, right? So it must either be f1 or f2. If that confuses you, again, we can talk about that in class. And then is less than or equal to, because I have a filled in dot right here, 2. And my last subdomain is where x is greater than 3. Sorry, x is greater than 2. Good. Now, what I need to find are what are these subfunctions. Well, if I look here, let's try and work from easiest to hardest. Looks like my easiest one here is my third subfunction. This is just a horizontal line. Looks like it's at the value y equals 3. So we can say that f3, and I'll rewrite this. You know what? I can erase this. That's fine. F3, I'll say equals 3. So our output equals 3 if our input is greater than 2. Good. So there is our third subfunction all covered. Next, we'll go to the linear function over here, our first subfunction. All we need to find, hopefully you're masters, you really should be masters, of y equals mx plus b at this point, right? I know that's taking you back. Y equals mx plus b, where our b is our y-intercept, where our slope is m, and here we could calculate our slope. It looks like it equals 1, right? That's rise over run. We'll go over that a little more in a future lesson if needed, although we really should be feeling pretty comfortable with this. So our slope should be 1. That is, we're looking at x plus 2. For our input for subfunction 1. And for subfunction 2, that looks like it's going to be our toughest one here that we're working with, but we can see here we might be able to recognize it's a quadratic function. It has a vertex at 0, 0, and it also has the point here. It has the point 2, 4, which you might recognize as being right on our base quadratic function. So f2 of x is nice and straightforward, just x squared. Right, again, we have all of our subfunctions here. We have all of our subdomains there. You should be able to, at this point, you should be able to try handling some of these functions here. We should be able to graph from an algebraic equation. You should be able to handle something like this, where you're practicing, where you're practicing interpreting an absolute value function, and you should be able to try. I want you to try this here. It might be a bit of a challenge, but trying to demonstrate algebraically a discontinuity, right? We demonstrated up above in example 2. Was it example 2? Yeah, in example 2 right over here, we demonstrated a continuity right here because we evaluated f2 at -2, and we also knew we didn't necessarily evaluate, but what we did is we evaluated f1 at -2, and then we also demonstrated a discontinuity by evaluating f3 at -2 and comparing that to f2 at -2. If that confuses you, again, we can go over that in class, but you should be able to handle the rest of this. Try it out.